Here's something counterintuitive. The bigger the black hole, the calmer, more stable, and less likely it is to get angry. In the energy filament theory, the four distinct layers of a black hole structure the outer critical skin, piston layer, destruction belt, and boiling core, all exhibited a clear trend as the size of the black hole increases. The larger it becomes, the more stable and flattened it is, and the less it resembles the monstrous force you might have expected. To help visualize this, imagine two pots. One is small, the other large. When you turn up the heat on a small pot, it bubbles furiously, splashing liquids everywhere. However, when you heat up a larger pot, even though it's boiling fiercely, the liquid moves more gently, spreading over a much larger surface area, resulting in a much gentler appearance. This same analogy holds for black holes. A small black hole's boiling core is like the violent, rapid bubbling in a small pot. The energy filaments are swirling intensely, and the piston layer moves quickly, with the pores of the outer critical skin being numerous and chaotic, making the black hole look extremely agitated. On the other hand, the boiling core of a larger black hole can be compared to the slow-moving simmer of a deep-sea slow-cooking pot. The same energy, but distributed over a vast volume, causes the fluctuations to be more spread out and gradually flattened. The piston layer in a large black hole moves slowly, like the steady breathing of a whale, and the pores in the outer critical skin open and close slowly but with fewer disturbances. The whole system becomes much denser, slower, and more composed, creating an overall calm appearance. Now, let's take a closer look at the supermassive black hole at the center of the Milky Way. From the outside, it may appear too quiet, almost like a stationary sculpture in the cosmos. But this is not because it's inactive. Rather, it's so large that all of its movements are naturally slowed down and smoothed out. The larger the black hole, the more unusual its behavior becomes. The dimensional mechanism of the black hole shifts into a state of self-stabilization. As a result, the fluctuations within the boiling core are diluted. The destruction belt's restructuring becomes more uniform. The rhythms of the piston layer deepen and slow, and the outer critical layer becomes thicker and more resilient to disturbance. The larger the black hole, the more it naturally stabilizes itself. Contrast this with smaller black holes. A smaller black hole's boiling core resembles a tiny pot on a fast flame, where the energy filaments are constantly swirling violently, and the piston layer follows suit. The outer critical skin is full of many tiny pores, giving the entire black hole an appearance of being quick to respond and somewhat agitated. Small black holes behave much like temperamental creatures, with small amounts of energy causing sudden explosions and bursts. In contrast, a large black hole is more like a silent, heavy behemoth. Its movements are less frequent, but each one is powerful and deeply felt. The bigger a black hole is, the less dramatic its movements become, and the harder it is to provoke. In fact, as a black hole gets larger, it becomes more like a quiet yet extremely dangerous cosmic well. Its vast size and mass make it much harder to disturb, leading to a peaceful, steady state that contrasts sharply with the more volatile behavior of smaller black holes. As we continue exploring the wonders of black holes, we will discover that these massive objects are capable of holding themselves together by relying on their self-stabilizing structure. Smaller black holes can be seen as temperamental, explosive entities, whereas larger black holes exude a quiet and unnerving calm. Their stability comes from their immense size, which naturally slows down their energy processes and smooths out their reactions. So why are large black holes so much more stable, quiet, and composed than their smaller counterparts? It all comes down to the interplay between the layers of the black hole and the energy mechanisms within it. As we'll explore in the next episode, larger black holes can be like slow-cooking pots in space. Their activity and intensity spread over a massive area, making them appear eerily still. By contrast, smaller black holes are like fast-moving pots on a high flame, with energy and reactions that are quick, intense, and highly agitated. In our next episode, we'll explore why black holes get hotter as they cook. Why, despite their size and stability, The outer layers of a black hole might actually become hotter. Stay tuned for more fascinating insights into the universe. Tap follow, share it on New Physics, Clear Universe.